this experiment, you can learn how to measure resistance using the Wheatstone bridge method.
The electric circuit set up on the workbench will allow you to measure the resistance of the fixed resistor using the Wheatstone bridge connection. But before an explanation of the circuit behaviour, let's check the connections made on the bench. As you see, a voltage supply is connected via a switch to an ammeter that measures the main current delivered to the circuit. The rest of the circuit consists of two parallel branches with resistors. The upper branch consists of two variable resistors. And the lower branch consists of a variable resistor and a fixed resistor. It is the resistance of this fixed resistor that we wish to obtain by measurements. The parallel resistor branches are connected back to the power supply. You can see as well a sensitive multimeter connected between the middles of both resistor branches. Now let's analyze the circuit. Assuming the direction of the currents as shown, you can notice current I5 that flows through the sensitive ammeter. Let's apply Kirchhoff's first law to the node A. Current I1 enters the node, so it has a positive sign. Current I2 exits the node, so it has a negative sign. And the current I5 is equal to 0, so we can neglect it. From this simple equation, you can see that current I1 is equal to current I2. In fact, it is simply the same current. The same procedure can be repeated at node B. Current I3 enters the node, so it has a positive sign. And current I4 exits the node, so it has a negative sign. Current I5, having 0 value, can be neglected. From the second equation, you can see that current I3 equals current I4. It is again simply the same current. We assume that there is no current flow between points A and B, so the voltages of these 2 points are the same. Let's apply Kirchhoff's second law to the highlighted loop. Starting from point A, we should add, with a positive sign, the voltage drop across the resistor R1, and with a negative sign, the voltage drop across the resistor R3. There is no current in the branch with the sensitive ammeter. So we come back to the node A. The sum of these two voltages must equal 0. Now let's repeat the procedure for the second loop. Starting from node A, we should add a voltage drop across the fixed resistor with a negative sign and across the variable resistor R2 with a positive sign. Again, according to Kirchhoff's second law, the sum of voltage drops around the closed loop must equal 0. If we now divide the first equation by the second, we obtain the following ratio equality. We can simplify this equation by eliminating I1 and I3. What we have obtained is the ratio between resistances of a Wheatstone bridge as a necessary condition for 0 value of the current I5. Using the equation obtained, it is easy to find the value of one resistance when the other 3 are known. For example, the resistance of the fixed resistor equals Use this equation during the experimental session to calculate the value of the fixed resistance. However, you must adjust the variable resistances if you want to obtain zero readings on the sensitive multimeter display. In the experiment, you can vary four quantities: the supplied voltage and the values of resistance of the variable resistors.
To switch the power supply on or off, click on its switch. You can change the output voltage by turning the knob. If the current increases too rapidly, reaching high values for small voltages, it indicates a short circuit somewhere in your layout. In such a case, switch the power supply off and check the circuit once again. If you don't do it, you can blow a main fuse situated at the right-hand end of the bench. But remember, before any fuse replacement, switch the main circuit breaker off. If you don't know why, press "Why switch the main circuit breaker off before fuse replacement?" If you know why, press "OK, I know why." Let's see what would happen if the main circuit breaker is on and there is no voltage indicated by the power supply display. This means that the main fuse must be burnt out. As you see, the main fuse cannot conduct any current because its wire is burnt out. There is no voltage on terminal B of the main fuse, but the voltage still exists at terminal A. If you touch the fuse now, you will get a shock. Your body is now a conductor between a point of high potential and ground with a zero potential. So remember, always before fuse replacement, switch the circuit breaker off. To change the value of the resistance of a variable resistor, move the resistor slider between points A and B. Current flows through that part of the resistor that is between the resistor slider and point B. The remaining part of the resistor is short-circuited by the upper rail.